All right, so now we are ready to do some calculations. Now that we understand the right-hand rule, and we know that if we have, let's go over the concept here. So if we have a magnetic field, if we have a magnetic field, there's a magnetic field, and this magnetic field just points like that. And then we place a charge within this magnetic field. There's some charge Q. And if we let this charge move at some speed v, so there's some v, this charge will set up its own magnetic field. So this charge here, as it moves, will set up its own magnetic field, and more or less it would point like this. It would be still circular, weaker here, and circular, but then weaker and weaker as you move forward. There would be, this charge would have its own magnetic field. That magnetic field would obviously have to interact with the external magnetic field B. And so the two fields would interact and they would generate some sort of a force. So this is the motivation, if you will, for the presence of this force. Now, obviously, if this charge is not moving, that is, if B is 0, then what you get out of it is that the force on this charge would also be, magnetic force on this charge would also be 0. The only reason you get some force acting on this charge is because this charge is moving. As it moves, it generates its own magnetic field, and then that magnetic field interacts with the other magnetic field, and there's some sort of that interaction generates the force. So the way you calculate this is, so this is the motivation, but the equation for the actual force is F, force F, and this is the magnetic force on charge Q, is equal to Q, the bigger the charge, the bigger the force, times the velocity. The bigger the velocity, the bigger the force, crossed with the magnetic field. The bigger the magnetic field, the bigger the force. So this is the equation. Now, if you just want the magnitude of the equation, or rather, if you just want the magnitude of the force, then you would do F equals Q B sine theta. For theta, it is the angle between B and B. So let's maybe draw a picture here. Suppose that you have a magnetic field that points like this. There's a magnetic field that points like that, and let's say that you have charge Q, and charge Q is moving at velocity v like this. The angle theta would be the angle between vector v and vector b, and that angle theta would be, you should be able to guess, it would just be, let me do this in white, it would be this angle here. This is the angle theta. Yeah, that's the angle between B and B. All right, so let's do a sample problem. Number 1. We're going to do a straightforward one just so that you see how this equation is applied. And let's say that we have, let's say that our magnetic field points like this, just points down. So this is the magnetic field B. And then let's say that the charged particle Q is moving at velocity v in this direction. This is the velocity v. And let's say that we're lucky enough where the angle here is actually given to us. So that this angle here is, let's say, it looks about 45, so 45 degrees. And now let's add a couple more things to the picture. So let's say that the magnetic field, a strong magnetic field of 2 Teslas. Let's say that the charge is some small thing, say maybe 10 microcoulombs. And then the velocity itself, well, let's say we know the magnitude of the velocity, so that v equals 400 meters per second. All right, now, and you're asked to calculate the actual force exerted on this charge as it moves at this specific speed to this specific field in this specific direction. So the way you would do it is you're asked to calculate the magnitude in this case, and so you would just do F equals Q B b sine theta. And so let's plug in the numbers. Charge is 10 microcoulombs, so this would be 10 to the minus 6th times the speed, which is 400 meters per second, times the magnetic field strength, which is 2 teslas, times the sine of 45. I'm using degrees here, so you want to make sure that you're in a degree mode. That would give me a force of, let's calculate this force, let's see what we get. Okay, so I got 5.7 times 10 to the negative third. And units would be newtons, because this is just a force. So this would be the magnetic force exerted on a charge that moves specific speed through a specific field in a specific direction. All right, now, if you are in my algebra-based physics class, then you won't have to worry about the vector equation, meaning this one. But, and so you can probably pause the video at this point or stop the video at this point. But if you happen to be in calculus-based physics class, then you will need to know how to use the other one as well. And so let's give you a problem that looks a little different. Let's say that it's still going to be a simple one, but let's just say that I give you something to the effect of, let's say that the magnetic field points something straightforward. So maybe it's 2 teslas, but in a j hat direction. This would be the same thing as 0, 2 teslas, 0. And let's say that we have the velocity vector being, give it something to the effect of, if this points up, then maybe we'll have this one. Do the following, maybe 400 I hat plus 300 j hat. And that of course would be the same thing as 400, 300, 0. And let's say that the units here we have, misstate the units. So here units you would have teslas for the units, and then here for the units you would have meters per second. And then the charge itself, let's say it's an electron. So Q is E, it's 1.6 times 10 to the minus. Oh, we don't want the electron because then it flips the direction of that. Let's say it's a proton. So the charge is a charge of a proton, but the charge of a proton amounts to the same value as let's do this. Absolute value of the charge of the electron, and then therefore we get a positive here. So this is minus 19 coulombs. And then let's draw it and then actually calculate this thing. So let's first draw it. Let's see if we can make sense out of it. So here's the y-axis. Here's the x-axis. And here's the z-axis. Magnetic field, let's draw the magnetic field in here. It just points straight up. Along the y-axis, I'm going to draw it like this. Here's the magnetic field E, and then maybe I'll add. Now the magnetic field should really be present everywhere. So I should draw it like this, and guess I'll do that. Trying to avoid blurring this picture too much, but that here's the magnetic field, just points like that. I'll do one. Magnetic field just points straight up. It's 2 teslas, 2 teslas everywhere. And then I have the charge. Let's say that the charge sits right at the origin. It's at the origin. It doesn't have to be at the origin. It could be somewhere else in space. As a matter of fact, maybe we will just actually place it somewhere else in space. So let's put it here. So here I have a positive charge. Let me change the color. Here I have a positive charge Q. And this thing is moving at the velocity that is 400 meters in the x direction, 300 meters in a y direction. You know what? Why don't we change this thing? And why don't we make this thing k instead? So let me that will make my picture a little clearer. So let's do this. Let's get rid of this thing. I'm going to call this k hat, and therefore this goes away. Let's see. So we're going to call this k hat, and that would imply that I have 0 here, comma 300, the last one. Now if I do this, then what I'm going to get is something a little simpler in terms of the velocity. So let's say that the velocity now will point that, let's see what we have. We have 400 meters in the x direction. We move out in this direction. And then we have 300 meters in the z hat direction or k hat direction. So here, good enough. This is the velocity vector here. Right, where this is in the plane of zx, horizontal plane here. So, so that's good. And now I can figure out the direction of the force. I could just use the right hand rule to figure this one out. So what I would have is velocity points here, the magnetic field points up, so the force would be perpendicular to that. I would have the force pointing, that's going to be tricky to draw. But if this is the magnetic field, if it points up like this, and here be the velocity. So you just use the right hand, rule. And so in that case, I can probably actually draw it. I might be able to get away with drawing it. I would have the fingers pointing like this. Then they will just like 4 fingers. And then the right hand, my thumb would have to point like this along the velocity vector. So there's that. And then from here, I can see that the force itself would have to point out of the palm of my hand, but well, wish me luck on this one. Here's this little rectangle that I have. The force would have to be perpendicular to the surface of this rectangle, pointing, well, give it a shot. Say that's not bad. We'll take the win. Here's force F. If you can picture it, great. And if you can't, well, this is the best I can do. So now let's actually calculate the force, because the unknown here in this case, maybe do, let's maybe draw this thing in white, because I tend to do that in white. Fix that. Here's force F. Right, it should be in this direction here, coming out of the palm of your hand. So let's calculate this force. The unknown is force, but in the vector form. Ask it like this, and then if you want it in the end, you can also calculate the magnitude. So well, let's go ahead and do that part. I'm gonna move this stuff up a little so we have more room. That should be enough. So the equation is F equals Q times V cross B. To figure this out, I need to first find the cross product V cross B. And so what I'll have here is I hat, J hat, A hat. Velocity vector is 400, 0 and 300, and then the magnetic field vector is 0 to 0. To do the cross product here, when you're done with the cross product, you're going to get the following. I hat times goes away, so it's minus 600. That's the end of the screen. Okay. Minus J hat. And now for the J hat, I'm going to get 0. Good. Let's make sure that that's the case. Yeah, I just get 0. And then plus K hat. So for the K hat, I'm going to get 800. All right, so this is my cross product. So in other words, what I get for the force F is F equals the charge of an electron, which is 1.6, for the charge of a proton, 1.6 times 10 to the minus 19th, times the cross product, and that came out to be minus 600 I hat plus 800 A hat. You just multiply this thing through and you end up with your force. So force F would be, let's finish the problem. So I'll state the answer, and then once we have the answer here, you can also calculate the magnitude of this vector. So we'll do that. Let me pause the video. Okay, so these would be the answers. Multiply them out. You can restate these vectors if you wanted to in the following form. You don't have to, fine as it is there, but 9.6 times 10 to the minus 17th newtons, comma 0 for the y, and then you have 1.3 times 10 to the minus 16th newtons, and this could be our final answer. Note that this corresponds to the picture we have here. You only have the x and the z components for that vector. I'm not going to draw anything else in here because that will make it too congested, but you only have x and z components for that vector, so it works. And here's the magnitude. All right, this will do for basic problems that introduce this equation here, F equals Q times V cross B, which the magnitude, this would be Q, V, B sine theta.